The Artemis II mission represents a historic milestone in human space exploration, marking the first time astronauts will journey beyond low Earth orbit to the Moon since NASA's Apollo program ended over half a century ago. Artemis II is a component of NASA's broader Artemis program, which aims to return humans to the lunar vicinity and eventually to the lunar surface and beyond. This crewed lunar flyby mission is scheduled to launch no earlier than March 6, 2026, following a series of critical pre-launch tests and technical verifications. The mission builds directly on the success of Artemis I, an uncrewed test flight around the Moon that demonstrated the capabilities of NASA's Heavy-Lift Space Launch System rocket and the Orion spacecraft. Artemis II will, for the first time, carry 4 astronauts aboard Orion, demonstrating life support systems, deep space operations, and spacecraft performance with humans on board, essential steps toward future missions. The Space Launch System, or SLS, stands as one of the most powerful rockets ever built, designed to propel Orion and its crew against Earth's gravity and toward a trajectory that will take them around the Moon. The mission's planned route, known as a free return trajectory, will send the Orion spacecraft around the far side of the Moon and then use lunar gravity to bring the crew safely back to Earth. Once in lunar vicinity, the astronauts will observe the Moon from closer proximity than during Apollo, potentially viewing previously unseen lunar terrain and far-side features. The crew comprises 3 NASA astronauts, Reed Wiseman, Victor Glover, and Christina Koch, and 1 astronaut from the Canadian Space Agency, Jeremy Hansen, exemplifying international cooperation in space exploration. Preparations for Artemis II have included rigorous training, spacecraft system tests, and simulations designed to validate every aspect of deep space human operations. The mission is intended to last approximately 10 days, with the crew returning to Earth after completing their lunar flyby and re-entry, testing Orion's heat shield and other systems under real conditions. Artemis II's successful execution will be a defining step toward Artemis III, which aims for a lunar surface landing and prolonged human presence on and around the Moon. Artemis II's progress toward launch has hinged on a sequence of rigorous tests of the Integrated Space Launch System rocket and Orion spacecraft, culminating in a key milestone known as the wet dress rehearsal. A wet dress rehearsal is a comprehensive pre-launch test where engineers fuel the SLS core stage with supercooled liquid hydrogen and liquid oxygen propellants and run through most launch countdown procedures, without astronauts aboard. Initial attempts at conducting the wet dress rehearsal in early February encountered significant technical challenges, including recurring liquid hydrogen leaks at propellant interface connections. These leaks were similar to issues experienced during the Artemis I mission and had historically caused delays, demonstrating the complexity of managing cryogenic propellant systems at the scale required for crewed lunar missions. Engineers took the leaks seriously, replacing seals, inspecting filters, and resolving critical fluid line issues before attempting a second wet dress rehearsal. On February 19, 2026, NASA announced that the second wet dress rehearsal concluded successfully, with the SLS rocket fully fueled, hatches closed, and key launch countdown procedures executed. This successful fueling test removed one of the major technical obstacles to launch and allowed NASA to target March 6th as the earliest launch date. Following the rehearsal, the Artemis II crew entered a 14-day quarantine period designed to minimize any risk of illness prior to their departure from Earth. NASA officials have noted that while the wet dress rehearsal success is a significant achievement, additional steps remain, including final launch pad operations, flight termination system checks, and a comprehensive flight readiness review. The mission remains contingent on meeting all safety and performance criteria. These preparations take place at NASA's Kennedy Space Center in Florida, where the SLS and Orion spacecraft are integrated, tested, and ready for launch atop Launch Pad 39B. The meticulous testing regime reflects decades of lessons learned in human spaceflight and the priority NASA places on crew safety and mission success. The Artemis II launch will be broadcast globally, marking a new chapter in lunar exploration. This process of troubleshooting, testing, and validation underscores the technical sophistication and high stakes involved in launching humans to lunar vicinity for the first time in over 50 years. The launch preparations have also generated widespread international interest in lunar science and exploration as humanity returns to Earth's nearest celestial neighbor. Although Artemis II will not include a lunar landing, The mission's scientific and technical objectives are foundational for future lunar exploration and for understanding both human and machine performance in deep space conditions. A primary objective of Artemis II is to demonstrate the performance of spacecraft systems with humans aboard in the environment of deep space. The Orion spacecraft, designated for this mission, will house the crew and provide life support, navigation, communication, and re-entry protection during the approximately 10-day mission. Particular attention is being paid to Orion's heat shield, a critical component that will experience intense thermal loads during Earth re-entry. Following the uncrewed Artemis I flight, NASA identified unexpected erosion and char loss in the spacecraft's ablative heat shield material, known as AVCOAT. Engineers have analyzed the behavior of this material under re-entry conditions and adjusted mission plans to mitigate risk, including modifying re-entry profiling to limit time in peak heating phases. The Artemis II crew will observe spacecraft performance and heat shield behavior under real mission conditions, providing data that will inform upgrades for future missions. Beyond spacecraft systems, Artemis II will also enable context for human physiological responses to deep space conditions. While not long duration, the mission will give researchers the opportunity to begin assessing how extended exposure to radiation and microgravity beyond low Earth orbit impacts astronaut health and performance. This information will be vital for planning sustained lunar surface missions and crewed expeditions to Mars, where time in deep space will be significantly longer. The mission also includes demonstrations of manual control of the Orion spacecraft during proximity operations with the interim cryogenic propulsion stage and practice docking procedures. These operations are essential rehearsals for future missions where Orion will rendezvous and dock with lunar landers or other spacecraft. Artemis II will also provide valuable operational experience, validating procedures, communication protocols, spacecraft interfaces, and ground support systems needed for more complex missions. NASA science teams anticipate that visual observations from lunar vicinity, including possible views of the far side of the moon, will complement data collected by orbiters and robotic missions. Given the far side's unique geology and lack of direct line-of-sight communication with Earth, imagery and observations gathered during Artemis II can enhance understanding of lunar formation and structure. The mission's scientific, technical, and operational outcomes will directly influence the planning and execution of Artemis III and subsequent missions that aim to return humans to the lunar surface and to establish long-term exploration infrastructure. While Artemis II itself focuses on demonstration and preparation for future surface missions, it arrives at a moment of heightened scientific interest in several long-standing lunar mysteries that continue to intrigue scientists worldwide. One such mystery involves the moon's geological activity and internal evolution. Observations from orbiters and landers over recent years have revealed that the moon is not completely geologically inert. Scientists have identified extensive networks of fractures and tectonic features across the lunar surface, indicating that the moon continues to cool and contract, producing moonquakes and other signs of tectonic stress. For example, recent studies have reported the discovery of more than 1,000 previously unobserved surface fractures, raising questions about the forces shaping the lunar crust and its tectonic history. Understanding the moon's current activity is essential for interpreting its formation, thermal evolution, and internal structure. Another area of active research relates to the composition and distribution of water ice and other volatiles in permanently shadowed regions, particularly near the lunar poles. Data from robotic missions have confirmed the presence of hydrogen and potential water ice deposits in craters that never see sunlight. These discoveries have profound implications for future human habitation, as water can serve as a resource for life support, fuel production, and radiation shielding. Exploring the South Pole Aitken Basin, one of the largest impact structures in the solar system, remains a priority because its ancient terrain holds clues to early impact history and the moon's deepest crustal layers. Recent studies have revised interpretations of major craters, suggesting more complex formation histories than previously thought, which impacts expectations for lunar geology and chronology. Scientific inquiry also continues into the origin of lunar surface materials and their potential links to Earth-Moon formation theories. Lunar rocks returned by Apollo missions, combined with remote sensing data and recent orbital spectroscopy studies, have shaped current models of how the moon formed from a giant impact early in Earth's history. Missions such as NASA's Lunar Reconnaissance Orbiter and other international assets provide ongoing high-resolution data that refine these models. Moreover, the concept of deploying lunar gravitational wave detectors and other advanced observatories on the moon's far side highlights the moon's potential as a unique platform for fundamental physics research. The far side's radio-quiet environment could enable precise gravitational wave measurements, opening new astrophysical windows. Artemis II, by returning humans to the vicinity of the moon and setting the stage for surface missions, plays a role in this broader scientific context. While the mission itself will not conduct surface science experiments, it will demonstrate the capabilities and procedures needed for humans to work effectively in lunar environments that will be the focus of future investigations into these enduring mysteries. Artemis II, thus, serves as a stepping stone, bridging robotic discoveries with human exploration that will deepen our understanding of the moon's past, present, and its role in the solar system. The success of Artemis II is critical not only for validating human deep space operations, but also for advancing NASA's long-term exploration architecture, which includes returning humans to the lunar surface and preparing for eventual human missions to Mars. NASA's next major mission in the program, Artemis III, aims to land astronauts near the moon's south pole, a region of intense scientific interest due to the presence of water ice and unique geological features. Artemis II's demonstration of spacecraft systems, life support performance, operational procedures, and crew responses provides the baseline data and confidence needed to undertake this next phase. Artemis III will require additional hardware, including a human landing system provided by commercial partners, capable of ferrying astronauts from lunar orbit to the surface and back. The operational lessons learned from Artemis II, including communication protocols, navigation practices, and deep space crew management, will inform the design and execution of Artemis III and subsequent missions. Beyond lunar surface operations, the Artemis program's long-range vision includes establishing a sustained human presence in lunar orbit and on the surface, enabling scientific research, resource utilization, and technology demonstrations that will feed forward to Mars exploration. Infrastructure concepts such as the Gateway, a crew-tended lunar orbiting outpost, will play a role in supporting longer and more complex missions. The Artemis Accords, a set of principles governing cooperation and civil space exploration among partner nations, underline international participation in lunar exploration efforts and reflect a collaborative approach to expanding human presence beyond Earth. Artemis II itself embodies this collaborative spirit through the inclusion of a Canadian astronaut and contributions from international partners to spacecraft systems and mission planning. Looking beyond the Artemis program, private and public actors are increasingly active in cislunar space and lunar surface missions, driving innovation in lander technologies, robotic precursors, and lunar resource prospecting. These activities complement NASA's goals and expand scientific and commercial opportunities. Human health research continues to evolve as Artemis missions increase time spent in deep space, enhancing understanding of radiation exposure, microgravity effects, and psychological factors associated with long-duration missions. Experience gained on Artemis II and future missions will be essential for preparing astronauts for the rigors of Mars transit and surface operations, where isolation, distance from Earth, and extended exposure to deep space conditions will be far more demanding. Artemis II stands at the gateway to this future. By proving that humans can safely operate spacecraft around the moon and return, Artemis II lays the foundation for a future in which sustained lunar presence becomes routine and Mars becomes within humanity's reach. Each phase of exploration, from rigorous tests on Earth to lunar flyby and surface missions, contributes to an expanding frontier where scientific discovery, technological innovation, and human curiosity converge.